In our previous lectures, we talked about the Lyapunov characterization of stability for autonomous systems. And the Lyapunov stability theorem was such that if you have a positive definite function for an autonomous system for which the origin is an equilibrium point, which has a negative, and that function, positive function has a negative definite derivative, time derivative, then we say the origin is asymptotically stable. Okay. And furthermore, if the Lyapunov function, your positive definite function, is radially unbounded, then the result is global, that is, the origin is globally asymptotically stable. In this lecture, we're going to extend that to non-autonomous systems. In particular, we'll study Lyapunov characterization of uniform stability, that is, what conditions should be satisfied by a Lyapunov function candidate so that we have uniform asymptotic stability and global uniform asymptotic stability. Note that for autonomous systems, we didn't have to use the word uniform, but for non-autonomous systems, there is a difference between uniform stability and stability alone. Uniform stability is a stronger result, likewise uniform asymptotic stability is a stronger property of the equilibrium point. And by uniform, roughly speaking, what we mean is that the worst case overshoot, for instance, does not depend on the initial time, or the worst case convergence rate does not depend on the initial time. Okay, so when that is the case, the stability and asymptotic stability, they become uniform. Okay. So the first theorem about uniform asymptotic stability is numbered 4.9 in our text, and you'll see how global uniform asymptotic stability can be established for a non-autonomous system. Okay, let the origin be equilibrium point for our non-autonomous system x equals f of tx, and the definition of an equilibrium point for the time there in right hand side was such that plug in x equals 0, for instance, we're checking the equilibrium pointness of the origin, plug in x equals 0, and the right hand side must be 0 for all times, for all t. Okay, if that is the case, we say the origin is an equilibrium point. And let this scalar valued function times Rn R be continuous differentiable function satisfying the properties which we will express in terms of comparison functions, which we introduced in one of our previous lectures. Function such that this Lyapunov function, which possibly is a function of time, not only state but also a function of time, is sandwiched between the norm of the state passed through two class K infinity functions. Okay, this alpha 1 and alpha 2, they're class K infinity functions, and the class K infinity function was simply function continuous 0 at 0 and strictly increasing. Furthermore, it should be unbounded, so that's a class K infinity function. Okay, so that's one thing, and so this is what should be satisfied by V. And as for V dot v dot tx, this is the time derivative of v, should be upper bounded by minus alpha 3 of x. Okay. And note that for Lyapunov function without time dependence, v that was simply the gradient, the inner product of the right hand side f with the gradient of v. But now we also possibly have explicit time dependence for our Lyapunov function. Therefore, to that inner product we also have to add partial derivative of v with respect to t. That is v dot tx is partial v with respect to time plus the inner product that we're familiar with. That can be t of x. Well, to avoid confusion, okay, by this number, we mean partial derivative with respect to x, so let me write it as partial v partial x, which is by definition or by convention is a row vector, and we're multiplying that by the column vector, which is our right hand side of tx. Okay, so this is what we mean by v dot. Okay, and these two conditions are to be satisfied for all times and all states, okay, x and rn, with some fixed alpha 1, alpha 2 k-infinity functions. Now that if alpha 1 is k-infinity and alpha 2 is k, automatically, since alpha 2 is lower bound by alpha 1, alpha 2 must also be a k-infinity function. Okay, so alpha 1 and alpha 2 must both be k-infinity functions, and alpha 3, it's okay, that is just a class k function. The difference between class k and class k infinity is that class k function doesn't have to go unbounded. It has to be strictly increasing, but it's allowed to be converging some finite value. Then, if these conditions are satisfied, we have global uniform asymptotic stability. It is global uniform asymptotic stability. Okay. And if these conditions are satisfied in some neighborhood of the origin, that is, if they're satisfied locally, then you have only uniform asymptotic stability. Okay. Now, note that in this characterization, we didn't use the word positive definite, we didn't use the word negative definite, we didn't use the word radially unbounded, okay? Those we all used when we were writing down a statement of the Lyapunov's theorem for autonomous systems, okay? But those things, positive definiteness, radial unboundedness, and negative definiteness, are contained in these conditions, okay? For instance, it's 0 at 0 because it's never negative, and it's pushed down by this class k infinity function, or the norm passed through this class k infinity function, okay, from above. Because if you plug in x equals 0, this norm of 0 is 0, alpha 2 of 0 is 0, because by definition, class k infinity function is 0 at 0. Therefore, v must be less than or equal to 0 when x equals 0. Since v cannot be negative, v must be 0. So it's 0 at 0. How about positive for elsewhere? Now, if x is different than 0, we now look at the left-hand side. If x is different than 0, then the norm of x is different than 0. And since this is strictly increasing, alpha 1 of norm of x is different than 0. In other words, it's positive. Therefore, whenever x and it's pushing v from below, therefore, whenever x is different than 0, v has to be positive. Okay? So that says the positive definiteness. As for radial unboundedness, as you increase x further and further, the norm of x increases further and further, and this is class k infinity function. it's unbounded, and this guy is increasing further and further. So that means V is radially unbounded. So in this inequality, we have post-definiteness and radial unboundedness for V. And clearly, in this case, we have the negative definiteness of V dot, okay? Because this is 0 only when x equals 0, alpha 3 being a class K function, and we have a minus sign in front. Therefore, this is always negative, okay? This is always negative, except for the case when x equals 0. And since this is upper bounding V dot, it means that V dot is always negative, except at the origin. So in the second inequality, we have negative definiteness. Okay, and then if those conditions are satisfied, the origin has to be globally, uniformly, asymptotically stable. Okay. Which the class KL function characterization was that x of t is always bounded by some class KL function, beta x of t0, and then we have t minus t0. Okay. So that was the class KL function characterization of global uniform atmospheric stability for the origin. Okay, now we're going to talk about a stronger version of theorem 4.10, namely, we will establish global exponential stability of the origin. And that's the next theorem, theorem 4.10 in the text. Global exponential stability, and by definition, it's uniform. Okay. Global exponential stability. Now suppose the conditions in the previous theorem, okay, theorem 4.9, hold. Suppose further than that, the alpha functions, class K functions, they satisfy some polynomial shape condition. Okay, suppose for that we can let alpha 1 of S is S, K1 S to the R. K1 S to the R. Alpha 2 S is some constant, positive constant, K2 times S raised to the power R, R being a positive power. And alpha 3 belongs also to the same family, that is some constant times S raised to the power R, or some K1, K2, K3, and R, all positive constants. Then the origin is globally exponentially stable. That is x of t, the norm of a solution is always upper bounded by some constant e to d minus lambda t minus t0 times the initial norm of the solution, where c and lambda, they are positive constants. So that was how we define global exponential stability. Okay, and as I said earlier, these theorems can be made local, okay, if the conditions given in these theorems, if they hold only locally in some neighborhood of the origin, then you can just drop this G, okay, and you have uniform stability of the origin, or exponential stability of the origin. Okay. Now let's prove the second theorem, which is a stronger result. And we'll see how easy it's to work with the comparison functions. Okay, so that was one of the motivations for us to introduce them. They make the analysis quite straightforward. Okay, so proof of the last theorem, theorem 4.10. Okay, so what we're given is the following, given that K1 norm of x raised to the power r. So this is r, alpha 1 of norm of x. And now since alpha 1 has this special structure, therefore the lower bound on our Lyapunov function is of this form, K1 times norm of x raised to the power r. Less than or equal to Vtx, and alpha 2 has the form, the same form, some constant times norm of x raised to the power r, K2 x raised to the power r. And V dot here of x is bounded by minus K3 norm of x raised to the power r. Okay, so we have some Lyapunov function, we're given some Lyapunov function which satisfies the following set of conditions. Okay, V satisfies this and its derivative satisfies that. And from this set of conditions, what we're trying to achieve is we want to reach global exponential stability. Okay, so given this, establish x of t c e to the minus lambda t minus t0 initial norm. That is, find some c and lambda, okay, both positive constants, such that this is satisfied for all t0 and for all xt0, for all solutions. Okay, so we start working with V dot. Okay. V dot is less than or equal to K3 norm of x to the r. Of course, by V dot we mean V dot t comma x of t, and this is less than or equal to minus K3 x of t. Okay, norm and then raised to the power r. And this is less than or equal to what? This is less than or equal to. Okay, so we look at this part now, and from that we can write norm of x to the r is greater than or equal to v over k2. Okay, I just divide both sides with k2, and then multiply now both sides with minus 1. So we have r, and the sign of, or the direction of the inequality changes, minus v over k2. So we have v dot equals, well, forget about k3, minus norm of x raised to the power r. Minus norm of x raised to the power r is less than or equal to minus v over k2. Okay. And we also had k3 here, therefore this is less than or equal to minus k3 over k2 times v. Okay. Now, for simplicity, let us introduce the following notation. Let's call mu as the ratio of K3 to K2. K3, K2, they're both positive, therefore their ratio is also a positive number, which we're calling mu. Okay, so what we have figured out, therefore, P dot is less than or equal to minus mu, okay, some negative number, times d. Okay. Now, if this were an equality, note that v is a scalar function. If this of time, now we consider it as such. If this was an equality, v that equals minus mu v, we can write down immediately the solution. Okay, v equals initial v times e to the minus mu t. Okay, or mu t minus t0. But now instead of equality, we have inequality. What can be said in that case? Okay, not surprisingly, this implies that v of t of x of t, okay, this whole thing we consider as a function of time. X of t is some arbitrary solution, starting from some arbitrary initial condition and arbitrary initial time. This is less than or equal to mu t minus t0 times initial v. And by initial v, we mean v of t0, comma x t0. Initial time and initial state. Okay. Now, if this was, as I said, if this was inequality, it's straightforward to go from this line to that line. But now we have inequality. Again, it's not surprising that we have this because v is a positive function, but it requires a demonstration which we will provide soon enough. So, going from this line to that line, what we use is so-called comparison method. Now this is to be demonstrated soon enough. Now suppose that this holds, we can proceed as follows. Then we continue as what? Okay, so concentrate on this thing, the last thing that we have figured out. Now, once again, we're looking at the first condition, okay, these inequalities. Now, this v, upper bounds k1 times norm of the solution raised to the power r. Okay, so therefore we can replace this by this guy without violating the inequality. Okay. So we have therefore k1 norm of x of t raised to the power r is less than or equal to this thing, okay, which we use this part. And then as for this guy, we can upper bound it. Again, we can use the other part. We can upper bound that by k2, then norm of x of norm of the initial state, x of t0 raised to the power r. Okay. And this is something positive, therefore it doesn't affect inequality. So what we can write is e to the minus mu t minus t0, and we replace this v, okay, by k2 norm of x t0 raised to the power r. Okay. And what's that written? Exponential stability immediately follows. Okay. All we have to do is rearrange the terms. We divide both sides with k1. K1 is positive, therefore the direction of inequality wouldn't change. And then we take the rth root of both sides. Okay. Still, that wouldn't change the direction of inequality because everything is positive. Hence, we can let, or we can leave on the left-hand side just the norm of x of t. And what we have is, this is less than or equal to k2 over k1 e to the minus mu t minus t0. Okay. And this has to be taken the rth root, and then here we have also the rth root. Then we have norm of the initial state, that x of t0. This means we have, according to the definition of global exponential stability, we have global exponential stability where this guy is our c constant in our definition, and this mu over r, and mu was k3 over k2, is our lambda. okay, the convergence rate or the worst case convergence rate. The result follows with C equals K2 over K1 1 over R. Okay, by C we mean C here in the definition of global exponential. And as for lambda, lambda is mu over R, and mu was K3 over K2. Therefore, lambda is K3 over K2 times R. Okay, so that ends the proof. Okay, for the sake of completeness, let's also prove, because it's an insightful proof, prove this comparison lemma, okay, which is about differential, not a differential equation, but a differential inequality. Here's a comparison lemma. V dot t, okay, a scalar function. V of t is less than or equal to gamma times V of t. Okay, so V is a positive or non-negative function of time. So if you have this, it implies V of t is always less than or equal to e to the gamma t minus t0 times the initial v. Okay, so this is what we're trying to prove, because that's what we use here. Okay, now here is the proof. What we do is we define a new function, u of t, as follows: e to the minus gamma t minus t0 times v of t. Okay, gamma is just a real number. This is a general result. Gamma doesn't have to be positive or negative. All we care about is that it's a real number. Okay. So we define u of t in terms of v of t as follows. Okay, now why we did that will become obvious in just two steps. First of all, this new function u of t that we generated has the same initial condition with v. Plug in t equals t0, this becomes 0, therefore this becomes 1, and what we have is u of t0 equals v of t0. Okay, so initially they are the same. Note that u of t0 equals v of t0. Then let's compute time derivative of u. U dot equals, okay, now this is u of t, how we define u dot equals this dot times v plus this times v dot. Now this dot is minus gamma e to the minus gamma t minus t0 times v plus e minus gamma t minus t0 times v dot. Okay. And v dot, this is always positive, and v dot is upper bounded by that guy. Okay. Therefore, this is upper bounded by v dot replaced by gamma vt minus gamma e to the minus gamma t minus t0 v plus gamma e to the minus gamma t minus t0 times v. Okay. Note that this and that, they have the same magnitude but opposite sign, and therefore this is 0. Now, what we have obtained is u dot is less than or equal to 0. Okay, therefore u dot is never positive, so that means u can never increase, u of t can never increase. It can perhaps sometimes remain constant, and every once in a while it decreases a little, but it can never make a positive slope, because u dot is less than or equal to 0. Now, u dot less than or equal to 0 implies that u of t is never greater than the initial value, u of t0. Okay. Now this implies what? U of t was defined as e to the minus gamma t minus t0 times v. Okay. And u of t0 is same as vt0. Okay. And then all we have to do now is transfer this term to the other side. Because this term is positive, it doesn't change the direction of inequality. And we have v of t never greater than e to the minus gamma t minus t0 times its initial value, which was what we were trying to prove. Now let's apply theorem 4.10 to a non-autonomous system to establish global exponential stability of its origin. Example. It's from text 420. So suppose that we're interested in the stability properties of the origin of this following second order non-autonomous system. x1 dot equals minus x1 minus g of t x2. x2 dot equals x1 minus x2. And assume that g of t, although it's time varying, changing with respect to time, it's always lower and upper bounded by some fixed real numbers. It's never negative, because it's always greater than or equal to 0 for all times, and it's never too large, it's always smaller than or equal to some fixed number k. Okay, so that's the condition on g, and here's a condition on g dot of t, never greater than g of t. Okay, and these hold for all t. This puts a constraint on how steep g of t every once in a while rise. Now this g of t can be a known function, okay, but it may also, depending on the situation, it may also represent some unmodeled, okay, effect in your system, which is possible. You have some resistance somewhere, let's say, and that the resistance varies with respect to time, because its temperature changes with respect to time, and temperature affects its resistance and things like that. So the resistance of that resistor changes, and you would like to study, or you would like to understand whether that change, certain fluctuations, but those fluctuations are regular in the following sense. Okay, so we have some conditions so that things cannot go too wild. Okay? And you want to understand whether under those fluctuations, okay, which you cannot account for, let's say exactly, can you still establish a symptotic stability of the origin. Okay, so that's a very, it's a possible situation that one encounters in real life. Okay, So what we're going to do is, we will try to show that the origin is globally exponentially stable by a Lyapunov function. And we don't have to choose a Lyapunov function because it's given. It's given as v of tx as x1 squared plus 1 plus gt x2 squared. Okay. Well, that's not called the Lyapunov function, but the Lyapunov function candidate. Now we have to figure out whether it satisfies certain conditions so that we can use it in our analysis. Okay. So what we have to do, therefore, if you want to establish global exponential stability by using theorem 4.10, we have to establish that V satisfies positive definiteness and radial unboundedness. Okay, the first condition that's given in terms of class K infinite functions alpha 1 and alpha 2, and also we have to check its derivative, which must be negative definite. And that positive definiteness and negative positive definiteness of V and negative definiteness of its derivative, if we can establish them by the same, or by class K infinite functions, that they have the same form. Okay, so K1 times S raised to the power some R, then we will have global exponential stability. Okay, so let's therefore begin with trying to show that this is sandwiched between some K1 norm of X raised to the power something and K2 norm of X raised to the power something. Okay, so we can write the following: norm of X squared. And suppose that we're working with Euclidean norm, x1 squared plus x2 squared. Okay, so that's what we mean by norm of X. Now this is clearly less than or equal to, for all possible states and for all times, V of T of X. Okay, because V of T of X is given as such. It's x1 squared plus 1 plus gt x2 squared. Now since gt can never be negative, this 1 plus gt is never smaller than 1. Okay? Therefore we have as Vt of x, x1 squared plus something larger than 1 times x2 squared. And clearly it upper bounds x1 squared plus x2 squared. Okay, so the lower bound is established. How about the upper bound? This is less than or equal to x1 squared plus 1 plus k x2 squared. Okay. Now this is again 1 plus gt. Now we use the other bound on gt to establish the right hand side. Gt is never larger than k, therefore v is never larger than x1 squared plus 1 plus k times x2 squared. Okay. And this is never larger than 1 plus k x1 squared plus 1 plus k x2 squared. And that we can write as 1 plus k times norm of x squared. 1 plus k times, okay, let me squeeze it here. 1 plus k times norm of x squared. Okay. Therefore, V is always greater than norm of x squared, always smaller than this 1 plus k times norm of x squared. Okay, so x squared less than or equal to v t of x less than or equal to 1 plus k norm of x squared. Therefore, the first condition in the theorem is satisfied, the positive definiteness and radial unboundedness of V. So, okay, note that this alpha 1 and alpha 2, the class K function, they are of the same form. Okay, k times s squared. How about for V dot? As for the derivative, we have V dot t of x equals partial v with respect to time plus the transpose of its, or its partial with respect to the state, okay, partial v over partial x1 and partial v over partial x2 times the right hand side of the system, which is here. Okay, that's our f of t of x. So let's write that down also. Partial v partial x times f of tx. Okay, which is now partial v over partial t. V is given here. There's only one thing that explicitly depends on time, and that's g of t. So partial v over partial t is g dot times x2 squared. Okay. G dot t times x2 squared. Now, what's that by? Partial v with respect to partial x1, it's simply 2x1. And then we have partial v with respect to, or partial v over partial x2, which is 2x2, 1 plus gt times x2. x2, okay, so here we have the row vector, and this row vector multiplies the right hand side of the system, which is over there, minus x1 minus gt x2 and x1 minus x2. Okay. Now we're going to compute this product, and hopefully by dealing with the terms using some small tricks, we will be able to upper bound v dot by a negative definite function. Okay. In fact, for global exponential stability through theorem 4.10, what we require is we require v dot to be upper bounded by some negative number times norm of x squared. Okay. So let's see if that's possible. Okay, so v dot t of x therefore equals, let's write this term in open form, g dot t x2 squared minus 2 x1 squared minus 2 gt x1 x2 plus 2 1 plus gt x1 x2, and finally this guy times minus x2, which gives us minus 2 1 plus gt x2 squared. Okay. Okay. Now, let's remember the properties of g, k, and g dot less than equal to g. Okay, so those were the conditions satisfied by g. Now, this equals, we will have some cancellation. Here we have minus 2g x1 x2. Here we have plus 2g x1 x2. Therefore, this term, that term, they cancel. And what we're left with is minus 2x1 squared minus 2x2 squared plus 2x1 x2 minus x2 squared 2g of t minus g dot of t. Okay. Now what? This thing here we can write as g of t plus g of t minus g dot of t. Okay. Now g of t is positive. G minus g dot is also positive, therefore positive number, another positive number regardless of t, therefore this sum is positive, and it has a minus sign in front, and x2 squared is also positive. Therefore this whole term can never be positive because of this minus sign in front. Therefore we can drop that and replace this by less than or equal to sign. And then what we have here is, this is always greater than or equal to 0, hence we can drop that term and write minus 2x1 squared minus 2x2 squared plus 2x1 x2. Okay, so v dot is always upper bounded by that. And now we have to, this is a nice term, it's never positive, this is also a nice term, never positive. But this could be either positive or negative, so we have to somehow get rid of it, and it's easy. You can write this as what? Minus x1 squared minus x2 squared, okay, minus x1 squared x2 squared, okay? This equals that, clearly. Now what this is x1 minus x2 squared. It's something, it's something that's never negative, okay? But it has a minus sign in front, therefore this whole thing is something that's never positive. Therefore it can be dropped, and this equality sign can be replaced by less than or equal to. And once it's dropped, we have minus x1 squared minus x2 squared, and that's no other than minus norm squared. Okay. So that's minus norm square of x. So v dot is always upper bounded by minus norm of x squared. Okay. That is v dot t of x less than or equal to minus norm of x squared. Okay, let's call this inequality number 2. And then we can write down the final sentence. Okay. By 1 here, established earlier, and 2, we have satisfied the conditions, or we have shown that V satisfies the conditions in theorem 4.10. Therefore, by theorem 4.10, we have global exponential stability of the origin. The origin is globally exponentially stable.